This is SpaceTime Series 27, Episode 9, for broadcast on the 19th of January 2024. Coming up on SpaceTime, the Dark Energy Survey's unique insight into the expansion of the universe, Europe's Einstein Probe lifts off on a mission to monitor the X-ray skies, and using Earth's magnetic field to understand key ancient historical events. All that and more coming up on SpaceTime.
Welcome to Space Time with Stuart Gary.
Back in 1998, astrophysicists discovered that the universe was expanding at an ever-accelerating rate. They attributed this expansion to a mysterious force they called dark energy. The universe has been expanding outwards ever since its creation in the Big Bang some 13.82 billion years ago. Now, initially, scientists hypothesized that the force of gravity from all the mass in the universe should be slowing down that rate of expansion. Eventually, depending on how much mass there is in the universe, the expansion would finally stop, leaving the universe in a steady state of perfect balance. Alternatively, if there was enough mass in the cosmos, then gravity could become the dominating force, causing everything to slowly begin to contract again, accelerating faster and faster, until eventually everything would crash together in what scientists describe as a big crunch. That could be followed by another big bang, then another big crunch, and so on. However, that view of the cosmos changed in the 1990s as astronomers began studying distant thermonuclear Type 1a supernovae. The stars which create these supernovae all explode at about the same mass, and consequently with the same explosive power and hence luminosity. So, by using the inverse square law, astronomers can determine how far away these supernovae are. Unexpectedly, astronomers found more than 50 of these supernovae were fainter than what they should be for their measured redshift. That is how quickly it's moving away from Earth due to the expansion of the universe, and consequently how far away they are. Some unknown force, which astronomers call dark energy, dark because they don't know what it is causing space-time to expand at an ever-accelerating rate. Now, it's worth pointing out the idea of a dark energy force isn't new. It was first invented by Albert Einstein back in 1917. See, like most scientists of his day, Einstein just naturally assumed that the universe was stable and everything in it was in balance, just as it should be. The trouble is his own field equations were showing that in such a universe, gravity would have been the dominating force, crushing everything together. Einstein felt he was missing something, but he couldn't work out what it was. So he simply invented an expansion force for the energy density of space, a sort of vacuum energy, if you will. It was designed to counter gravity in his gravitational field equations, thereby creating a cosmological constant to return the universe to a steady state. However, Einstein was forced to abandon the idea of a cosmological constant in 1931 after astronomer Edwin Hubble discovered that everything in the universe really was expanding away from everything else, and the further away from us something is, the faster it's expanding. This forced Einstein to describe his cosmological constant as his biggest blunder. The recent discovery that the rate at which space-time is expanding is accelerating has now resurrected the cosmological constant, which, if correct, would ultimately lead to what astronomers are calling the Big Freeze, in which all the galaxies would eventually expand so far away from each other, only our local galactic group would remain together in what would be a very cold, dark and empty universe. And if that's not frightening enough, a more extreme version of dark energy, called phantom energy, could see the forces involved increase so much that they would eventually lead to what scientists are calling the Big Rip. A big rip would see the expansion of space-time occur not just on the cosmic scale of relativity theory, but also on the subatomic scale of quantum mechanics, ripping apart atoms into the constituent protons, neutrons and electrons, and even overcoming the force of gluons inside protons and neutrons to rip off quarks. Now, 25 years after the initial discovery of dark energy, scientists working on the Dark Energy Survey have released the results of an unprecedented analysis using the same technique to further probe the mysteries of dark energy and the expansion of the universe. The Dark Energy Survey is an international collaboration comprising more than 400 astrophysicists, astronomers and cosmologists from more than 25 institutions around the world, led by members of the US Department of Energy's Fermi National Accelerator Laboratory. The survey mapped an area almost 1/8 of the entire sky, using a specially built dark energy camera, a 570 megapixel digital device built by Fermilab and funded by the US Department of Energy's Office of Science. It was mounted on the Victor M. Blanco telescope at the National Science Foundation's Cerro Tololo Inter-American Observatory, a program of the National Science Foundation's NORI lab. They've been able to place the strongest possible constraints on the expansion of the universe ever obtained with the Dark Energy Supernova Survey. Their report in the Astrophysical Journal has covered some 1,500 new high redshift Type 1a supernovae using the full 5-year dataset of the survey. And the results are consistent with a now standard cosmological model of the universe with an accelerated expansion. Yet the findings are not definitive enough to rule out a possible more complex model. The Dark Energy Survey scientists took data for 758 nights across 6 years. To understand the nature of dark energy and measure the expansion rate of the universe, the scientists performed analysis with 4 different techniques, including the supernova technique used in 1998. Astrophysicists traced out the history of cosmic expansion with large samples of supernovae spanning a wide range of distances. For each supernova, they combine its distance with a measurement of its redshift. They can use that history to determine whether the dark energy density has remained constant or whether it's changed over time. Dark Energy Survey Director Rich Crone from Fermilab says that as the universe expands, the matter density goes down. But if the dark energy density is constant, that means the total proportion of dark energy must be increasing as the volume decreases. The standard cosmological model, known as lambda cold dark matter, is based on dark energy density being constant over cosmic time. It tells us how the universe evolves using just a few features, such as the density of matter, the type of matter, and behavior of dark energy. The supernova method constrains 2 of these features very well, matter density and a quantity called W, which indicates whether the dark energy density is constant or not. Now, according to the standard cosmological model, the density of dark energy in the universe is constant, which means it doesn't dilute as the universe expands. Now, if this is true, then the parameter represented by the letter W should equal -1. And the result found for W was minus 0.80, plus or minus 0.18, using supernova data alone. Now, combined with complementary data from the European Space Agency's Planck telescope, W reaches the -1 within the error bars. But those error bars are important. It means W is tantalizing but not exactly on -1. But it's close enough that it is consistent with -1. Still, a more complex model might yet be needed in order to determine if dark energy may indeed vary with time. To come to a definitive conclusion, scientists will need more data. Problem is, the Dark Energy Survey won't be able to provide that data because the survey stopped taking data in January 2019. The final Dark Energy Supernova analysis made many improvements upon the survey's first supernova result, which was released in 2018. That used just 207 supernovae and 3 years of data. For the 2018 analysis, scientists combined data about the spectrum of each supernova in order to determine their redshift and to classify them as a Type 1a or not. They then used images taken with different filters in order to identify the flux at the peak of the light curve, a method called photometry. The problem is spectra are hard to acquire, requiring lots of observing time on the largest telescopes, and that will be impractical for future dark energy surveys like the Legacy Survey of Space and Time, which will be conducted on the Vera C. Rubin Observatory. So the new study will pioneer a new approach using photometry, with an unprecedented 4 filters being used in order to find the supernovae, classify them and measure their light curves. Follow-up spectroscopy of the host galaxy using the Anglo-Australian telescope at Siding Spring will provide precise redshifts for every supernova. The use of the additional filters will also enable data to be more precise than previous surveys. It's all a major advancement compared to the original 1998 supernova samples, which only used one or two filters. The Dark Energy Survey researchers used advanced machine learning techniques and artificial intelligence to aid in supernova classification. Among the data from about 2 million distant galaxies observed, the Dark Energy Survey found several thousand supernovae. Scientists ultimately used 1,499 Type 1a supernovae with high-quality data, making it the largest, deepest supernova sample for a single telescope ever compiled. Back in 1998, astronomers used just 52 supernovae to determine that the universe was expanding at an accelerating rate. So when you think about it, it's really been a massive scale-up in just 25 years. Of course, there are minor drawbacks with the new photometric approach compared to spectroscopy. Since the supernovae do have spectra, there's greater uncertainty in classification. However, the much larger sample size enabled by the photometric approach more than makes up for this. The innovative techniques the Dark Energy Surveys pioneered will shape and further drive future astrophysical analyses. Projects like the Vera C. Rubin Legacy Survey of Space and Time and NASA's Nancy Grace Roman Space Telescope will pick up where the Dark Energy Survey left off. This report from Fermilab and the United States Department of Energy.
I'm a member of the Dark Energy Survey Collaboration, and I'm here on Cerro Tololo working to help commission the new Dark Energy camera that we've just installed on the Blanco telescope. The whole purpose of our project is to understand what is dark energy. Dark energy was discovered using, in part, this very telescope. And it was discovered by its effect on the universe. So dark energy is our name, and it's just a name that we give to the phenomenon that's causing the universe's expansion to accelerate.
We're not trying to figure out if dark energy exists. We're not trying to find it. We know dark energy exists. We're trying to characterize it. We're trying to understand what it does to us, what it does to the universe, to its expansion rate, and to the gravitational attraction of things like galaxies.
I work with the Dark Energy Survey, and I am working on SISP, which is the software end of the camera. And right now we are in the control room for the camera. We're doing a survey, so we want to cover a large section of the sky.
Over 5 years, the Dark Energy Survey will scan 5,000 square degrees of sky, far back in time and far away from us, in order to measure the distances of supernovae and the distributions of galaxies.
Since we're covering a large section of the sky, we've got to move the camera to cover all of it, and we have to track the sky as it moves because the sky moves very fast, and we're doing long enough exposures that if we weren't following the sky as it moved, it would get blurry. We are at an observatory, and we're looking at the stars, and you don't see the stars in the daylight. So generally, the observers will start working sort of around twilight, around dinner. You can start taking some calibration frames and dome flats. You can do those when the daylight's out. But you can't open the dome till after dark. And so right now, it's about 12:20, and this is very early in the night for an astronomer. And so an astronomer will generally stay here and work until sunrise when you can't take any more data.
Every time I come to Cerro Tololo, I realize how special an experience it is. Last night when we were looking up at the sky and when you could see the Milky Way so clearly, but you know that as a galaxy it's a line. You know that the plane of it is a line, and you see it curved across the sky. What else can that do to you but make you feel like you're on this sphere with all these other people, with the people here on the mountain, but everyone else. Like, you know that you're home in so many ways.
This job is a whole lot of fun. I've really enjoyed seeing at first, all I was seeing was the software, and it was very abstract, and it's been really neat to see first the telescope simulator being built at Fermilab, and then just to come here to Chile and be able to actually see the telescope take data. It's really exciting.
In some sense, the purpose of our experiment and what we'll learn by understanding more about what dark energy is to find out about the fate of the universe. What is going to happen into the future? Is the universe really going to keep expanding faster and faster and faster, or not?
Over 300 people, from professors to engineers to students and postdocs, putting together the Dark Energy Survey and all the infrastructure from simulations to theory and everything that went into making the survey possible. One might think, oh, I'm just one little piece in this large process. But when you think again about what we're exploring, when you think about the images that we're going to take, when you think about how far and away and how far back in time we're going to look, you can't help but feel like you're a part of something that's really important, that's helping us see not just about the past of the universe, but the past of us, where we've been and really where we're going to go.
And in that report from Fermilab in the US Department of Energy, we heard from Aaron Rudman from the Stanford Linear Accelerator Center, Brian Nord from Fermilab, and Anne Elliott from Ohio State University. This is SpaceTime. Still to come, Europe's Einstein Probe lifts off on a mission to monitor the X-ray skies, and using Earth's magnetic field to better understand ancient historical events. All that and more still to come on SpaceTime. The European Space Agency, the Max Planck Institute and China have joined forces to launch the new Einstein X-ray Space Telescope into orbit. The Einstein Observatory will survey the sky, hunting for bursts of X-ray light and other high-energy astrophysics from objects such as neutrons, stars and black holes. The mission was launched aboard a Long March 2C rocket from the Xichang Satellite Launch Center in Sichuan Province in southwestern China. The 1,450-kilogram probe was placed into a 600-kilometre high orbit, circling the planet every 96 minutes at an inclination of 29 degrees, thereby allowing it to monitor almost the entire sky in just 3 orbits. Over the next 6 months, mission managers will test and calibrate the instruments before its initial 3-year scientific mission begins. The probe is equipped with both a wide-field X-ray telescope and a follow-up X-ray telescope. The optics of the wide-field X-ray telescope were inspired by the compound eyes of lobsters in a modular layout employing hundreds of thousands of square fibres that channel light onto the detectors. This gives the probe the unique capability of observing nearly a tenth of the celestial sphere in a single glance. New X-ray sources spotted by the wide-field X-ray telescope can then be targeted with a follow-up X-ray telescope, which has a narrower field of view but is more sensitive and able to capture more details. The ability of the Einstein telescope to spot new X-ray sources and then monitor how they change over time is fundamental to improving science's grasp of some of the most energetic processes in the universe. These include powerful blasts of X-rays that occur when neutron stars collide, when supernovae explode, and when matter is swallowed by black holes or ejected by the crushing magnetic fields that envelop black holes. The Einstein Probe will also enable scientists to catch X-ray light from collisions between neutron stars and find out what's causing some of the gravitational wave events detected. Often, when these elusive space-time gravitational wave ripples are registered, astronomers are unable to locate the sources quickly enough. But by promptly spotting a burst of X-rays from one of these events, scientists might be able to better pinpoint the origin. This is SpaceTime. Still to come, using Earth's magnetic field to better understand key ancient historical events. And later in the science report, the new study that identifies the bacteria that inhabits human ear piercings. All that and more still to come on SpaceTime. Archaeologists have used changes in Earth's magnetic field to provide the most accurate yet dating techniques for archaeological finds. The new technique, which has been reported in the journal PLOS ONE, scientifically corroborates an event first described in the Old Testament's second book of Kings, the conquest of the Philistine city of Gath, now Tel Es-Safi in central Israel, by Hazael, king of Aram. The method, developed by Tel Aviv University, the Hebrew University of Jerusalem, Bahrain University and Ariel University, is based on measuring the magnetic field recorded in burnt bricks, which were the primary building material of the time. The new findings are important for determining the intensity of the fire and the scope of destruction in Gath, which was the largest and most powerful city in the region at that time, and also for understanding the construction practices of the day. See, throughout the Bronze and Iron Ages, the main building material in most parts of the land of Israel were mud bricks. This cheap and readily available material was used to build the walls of most buildings, sometimes on top of stone foundations. But during the same time, dwellers of other lands, such as Mesopotamia, where stones were hard to come by, would fire mud bricks inside kilns in order to increase their strength and durability. This technique is mentioned in the story of the Tower of Babel in the book of Genesis, where it states, and I'm quoting here, "They said one to another, 'Come, let us make bricks, and fire them thoroughly.' So they used bricks for stone." Genesis 11:3. Most researchers, however, believe this technique didn't reach the land of Israel until much later with the Roman conquest. It was also during the time of the Roman conquest that the land of Israel was renamed Palestine, or Philistia to be more accurate. But until the Roman conquest, the inhabitants of Israel used sun-dried mud bricks. The new magnetic earth dating method relies on measuring the magnetic field recorded and locked into a brick at the time it was burned and cooled down. See, the clay from which the bricks were being made contained millions of tiny ferromagnetic particles, minerals with magnetic properties to behave like very tiny compasses or magnets. In sun-dried mud bricks, the orientation of these magnets is virtually random, so that they cancel one another out. Therefore, the overall magnetic signal from a brick which has been dried in the sun is weak and not uniform. But by heating a mud brick to 200 degrees Celsius or more inside a kiln, it releases the magnetic signals of these magnetic particles, and statistically, they tend to align with the Earth's magnetic field at that specific time and place. So, when the brick cools down, the magnetic signal remains locked in that new position, and the brick attains a strong and uniformly oriented magnetic field, which can be measured with a magnetometer. Then, by reheating the bricks in a lab under controlled temperatures and magnetic field conditions, the brick's magnetic signature slowly begins to break down again, and scientists can then determine the temperature at which the bricks were initially fired. So, when bricks are found in an archaeological excavation, scientists need to determine if the bricks were first fired in a kiln prior to construction, or if they were fired in situ, in, say, a destructive event during the burning down of a city. In this way, this new method can provide a conclusive answer, which is crucial for correctly interpreting the findings. The new technique can also determine the orientation of the Earth's magnetic field when the bricks originally cooled down. Now, in Israel, this means north and downwards. But when builders take bricks from a kiln and then build a wall, they'll lay them in a random orientation, thus randomizing the recorded signals. On the other hand, when a wall is burned in situ, as would happen when a city is being destroyed by an enemy, the magnetic field of all the bricks would be locked in the same orientation. The real test came when the new method was applied to the Tel Es-Safri archaeological ruins. The prevalent hypothesis, based on the Old Testament, historical sources, and carbon-14 dating, attributes the destruction of the structure to the devastation of Gath by Hazael, king of Aram, Damascus, around 830 BCE. However, a different paper proposed that the buildings had not been burned down, but had simply collapsed over decades, and that the fired bricks found at the structure had been fired in a kiln prior to construction. Now, if this hypothesis were correct, it would be the earliest instance of brick firing technology discovered in the land of Israel. To settle the debate, the authors simply applied the new method to samples from the wall at the dig site and to collapsed debris from around the site. And the findings were conclusive. The magnetic fields of all the bricks in the walls and the collapsed debris around the walls all displayed the same orientation, north and downwards. That means that the bricks were indeed burned and then cooled down in situ, right where they had been found, namely in a configuration in the structure itself, which collapsed within a few hours. Had the bricks been fired in a kiln and then laid in the wall, their magnetic orientations would have been random. Furthermore, had the structure collapsed over time and not in a single fire event, the collapsed debris would also have displayed random magnetic orientations. So, what does it mean? Well, it means the account in the Bible's Old Testament is essentially correct. These findings are important for deciphering the intensity of the fire and the scope of the destruction of Gath, the largest and most powerful city in the land of Israel at the time, as well as for understanding the building methods which were used at the time. In other words, the findings indicate the brick firing technology was probably not being practiced in the land of Israel at the time of the kings of Judah and Israel. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with the Science Report. A new study has found that kids and teens with autism are less likely to undertake physical activity and have worse sleep patterns than kids and teens who aren't on the spectrum. The findings, reported in the Journal of the American Medical Association, found that kids with autism spectrum disorder take longer to fall asleep after lights out, slept for shorter amounts of time, and had less efficient sleep than their peers. The gap in physical activity levels between kids on the spectrum and their peers also got bigger as kids got older, which could be because kids on the spectrum are less likely to participate in sports with higher social demands such as basketball, football, and volleyball. Scientists have discovered that fairy wrens will help raise a relative's babies in the hope of having an affair with their relative's partners. Some fairy wrens have been seen forgoing having their own chicks in order to help others raise their brood, something known as cooperative breeding. But the motive for this apparently altruistic behaviour has always intrigued scientists. Now, a report in the Journal of the Royal Society Open Sciences found that these helpers would only help a relative and were most likely to help breeding pairs that contained both a relative that was of the same sex as them and a potential mate. The authors suggest that the helpers are getting some indirect benefits, such as social bonds from helping the reles, and that some are even getting some direct benefits, possibly from a potential mate. Dear oh dear. Scientists in Canada have uncovered the bacteria that inhabit human ear piercings. They found that even though people have their skin sterilised before a piercing, these sites regularly end up with a greater diversity of bacteria living there than on regular earlobe skin. And the process of piercing changes the local microbiome. The new findings, reported in the Journal of the Proceedings of the Royal Society B, showed that the piercings cause a shift towards a moist skin microbiome, which they say could be because the piercings can potentially trap moisture. The authors say that as well as being a form of cultural, religious and personal expression, ear piercings also represent a form of ecosystem self-engineering of the ecological landscape of the human skin. A British newspaper has used an image of the Shroud of Turin and applied a little artificial intelligence in order to find out exactly what Jesus might have looked like. However, as Tim Mendham from Australian Skeptics points out, the first problem is whether the shroud itself is real.
We're talking about the shroud. Someone just wanted to know what Jesus looked like, and as you will have seen from most European representations, he doesn't look like a Middle Eastern person. Looks more like a Norwegian person, a blonde sort of Aryan look about him.
Norwegian Hasidic Jew.
That's the one, yeah. It's an interesting idea. So anyway, trying to think what Jesus looked like. I'm not going to go into the fact, did Jesus exist? Let's assume he did. What did he look like? Some have suggested that he looked very Middle Eastern, sort of dark hair, bearded. Someone applied artificial intelligence assessment to the Shroud of Turin. Now, the Shroud of Turin is supposedly, the story goes, the material that was wrapped around Jesus, when he was put in the cave, in the tomb, etc., and that for some particular supernatural reason, his image was transmitted onto the shroud itself, an electrical discharge, a chemical reaction, whatever. And the shroud was first noticed in about the 1200s, 700s, something like that. That's when the first references come to it. There was a local bishop who said, there's this guy showing this cloth around, reckons it's the shroud of Jesus, etc., and that we should stop him. Anyway, the church didn't, and it kept on appearing and going through private hands, and eventually ends up in the cathedral at Turin in Italy, where they show it every 40 years, and you get millions of people coming through to have a look at it. The image of Jesus, which is a bit hard to see. It's not very clear, but if you photograph it, turn it into a negative, etc., you can apparently see it better. So, UK Daily Star got an AI specialist onto it and looked at the image, obviously not the shroud itself, but looked at an image, and then processed it and created a 3D version of it. This is not particularly difficult. I think they've been doing this with landforms for years. So they did this with the face, pull it up, and you think, that's what Jesus looks like. Well, no. First of all, the shroud is probably not real. It's not really of Jesus, and therefore the image on the shroud is probably not Jesus. It's probably not even a true shroud. In fact, the suggestion it was made at the time of his medieval age. You could do the same with a Mona Lisa or anything like that to see what she actually looked like. But this is Jesus, so it's probably more important. Yeah, it's a problem with AI that it's sort of people give it more credence, more sort of special notice than it really deserves. Because in this particular case, it's nothing more than a computer-generated image, which is pretty easy to do, I think, if you have a bit of technology to hand. But just mention AI and everything becomes very exciting, super-duper sort of impressive results. There's a video of the generation of this image, which goes through variations of all different sort of looking Jesus, from a Middle Eastern person to a Northern European person to fat, thin, bald, hairy, whatever, which just goes to show that you can generate any sort of image you like. If you remember the technique of morphing from one photo to another, and you can see the different stages between computer-generated imagery. I think Michael Jackson used it in a video clip for one of his songs. And you go from face to face to face to face, and you're morphing from one face to the next. It doesn't necessarily show that Jesus exists, and the very fact that you can do this from this one source indicates that you can do basically anything.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.